Hello and welcome to today's video. In this video and the next few videos, we're going to talk about determinants. The basic idea here is we want to know whether a matrix can be inverted or not, so whether it has full rank or not. And there is a measure that tells us that. This measure is going to be the determinant. Of course, the determinant also has other uses, and we'll come back to it at some later point. But for now, we'll just regard it as a measure that says us something about the invertibility of a matrix. We've already briefly touched upon this subject for 2x2 matrices, so you might recall how that went. I'll give it to you in a second. Let's first write down the heading of this chapter. So this is determinants. As a brief reminder, if we have a matrix A of this form here, A11, A12, A21, A22, so a 2x2 matrix, then remember we've tried to find the inverse of that matrix, and one condition that we encountered here was the matrix must of course have full rank, and that was dependent on a certain number. Remember we have rank of A equals 2 if and only if what we called D, and that was A11, A22 minus A21, A12, if that was not 0. So you could say this number here, this D here, this is an indicator of full rank of our matrix A. And this is basically the role that the determinant will play. And it will turn out that this precise expression here is actually the determinant of a 2x2 matrix. We'll first define the determinant in a little more general framework, and then we'll apply that to 2x2 matrices and also to an example of a larger size. So let's first have the formal definition. Let's say we have a matrix A with components Aij that is a square matrix. So in n by n. And the determinant is only defined for square matrices. Before we can actually write down the formula for the determinant, we need to have a little terminology. That is, for n at least 2, we define a so-called Aj cofactor. Like this, Ij cofactor, and we will write this as Aij of the matrix A. And this cofactor is simply going to be the matrix that we obtain from A by deleting the ith row and the jth column. So we reduce the matrix by one row and by one column, and we denote the index of that row and of that column by I and j respectively. And the resulting n-1 by n-1 matrix is then called the Ij cofactor. So this is defined as the n-1 by n-1 submatrix obtained from A by deleting the ith row and the jth column. And with these cofactors, we can now formally define the determinant. So we'll say the determinant, we'll abbreviate that as det of A is a real number that is recursively defined as follows. First, the easy case. So if we have n equals 1, meaning A consists of just one entry, A11, then we set the determinant to just this number. So in that case, the determinant of A is defined as A11. That's the base case. And for larger matrices, we define the determinant by means of those cofactors. So we reduce the relevant size, and we can repeat this step again and again and again until we end up at matrices of size 1 by 1. So more precisely, for n at least 2, we set the determinant of A to be the following sum from I equals 1 to n minus 1 to the power of I plus 1 times the entry AI1. So first column, 1 here, that denotes the column, and then I here denotes the row. So we go down the first column as we increase this I. And we multiply this by the determinant of the cofactor I1. So for these cofactors, we always delete the first column and we delete the ith row. And that means we define the determinant of an arbitrarily large matrix by a sum over determinants of matrices that are one smaller. And we just repeat this process until we get to matrices of size 1. And then we can use the first part of this definition and just use the number in the matrix as its determinant. So this is the formal definition here. We'll talk about methods of computing the determinant later on. This is one possible method. It's not the only one. There are others, and we'll see examples for that as well. But before we do that, let's first see 2 examples of actually applying this formula here, so that you get an idea of what this is about. First example, let's revisit our 2 by 2 matrix first to see that this actually does the right thing. So remember, this was our general 2 by 2 matrix. And we want to determine the determinant of A. Then we have to determine the cofactors first. So what we need here is the determinant of A. Remember, that is the sum from 1 to n. N is 2 in this case. Of minus 1 to the I plus 1 times AI1 times the determinant of the cofactor AI1. So more precisely, what we have here is for I equals 1, we get minus 1 to the 1 plus 1 times A11 times the determinant of the cofactor A11 plus minus 1 to the 2 plus 1 times A21 times the determinant of the cofactor A21. So minus 1 to the 1 plus 1 is plus 1. A11 is just A11. Now for this cofactor here, what is this cofactor A11? Let's talk about that first. You get that by deleting the first column and the first row. So we would remove this first column and this first row here, this and that. And what remains is our reduced matrix. So what remains is just A22. So that is this cofactor. And here we get minus 1 to the power of 3. So that's a minus 1 times A21 times the determinant of another cofactor. This time it's A21. So we get that by deleting the second row. That's the first two here. And the first column. And what remains is this entry, A12. So what do we get? Well, this is A11 times A22 minus A21 times A12. And you'll remember, hopefully, this is precisely the formula that we started with. There's a neat help to remember this formula. So if you look at the matrix once again, looking like this here, then what we do is we first multiply these two entries here, and those get assigned a plus, so those are counted positively. And then we multiply these two entries here, and those are counted with a minus, right? So that's how you can hopefully remember that formula more easily. It's the product of these two minus the product of these two. So that's the formula that you can use for 2 by 2 matrices, and only for 2 by 2 matrices. Larger matrices are more complicated, and we'll see that as an example in just a second. So let's move on to a larger matrix, part B. Let's say we'd like to know the determinant of this matrix here, 1, 2, 1, 3, 7, 4, 4, 10, 9. I'm just going to apply the formula. So the determinant of A is, let's copy that matrix once again. So remember, we have to look at the first column, and there is a summand for each entry in the first column. So we'll have one summand corresponding to this entry here. We'll have one summand corresponding to this entry here. And we'll also have one summand corresponding to this entry here. So let's start with these. The first summand will be minus 1 to the power of I plus 1. So this is 1 plus 1 times the actual entry, that's a 1, times the determinant that we obtain by removing the first row and the first column. Let's copy that whole thing once again. 3, 7, 4, 4, 10, 9, like this. And then remember, we have to remove the first column and also the first row. The position of that entry here tells us which row and which column we remove. So what remains is this matrix here. Now let's do the same thing for the green entry. So we'll add we'll add -1 to the power of row. The row number is now 2 plus 1. And you notice 1 is the column number, of course. Times the actual entry, which is a 2, times the determinant of, let's see what remains here. So now we have this entry, and that means we have to delete again the first column, and now we delete the second row. So what remains is this row and this row. That's the matrix that we will have left there. And finally, let's also have a look at the last row. So here we have a -1 to the power of 3 plus 1. We're in the third row, that's where the 3 comes from, plus 1 for the first column. Times the actual entry, that is a 1 here, times the determinant of, let's copy that once again. So 1, 2, 1, 3, 7, 4, 4, 10, 9. And we'll remove what corresponds to this entry. So we'll remove the first column and we'll remove the last row. And that means this part here is what remains. Okay, so let's copy what we have here. The orange part, that's -1 to the power of 2 times 1 times the determinant of 7, 10, 4, 9 plus the green part, that is -1 to the power of 3 times 2 times the determinant of 3, 4, 4, 9 plus the last part here, -1 to the power of 4 times 1 times the determinant of 3, 4, 7, 10. So what we get in the end, -1 to the power of 2 is +1, of course, times 1 is still +1, times that determinant. And that determinant, well, that is, remember, we multiply these two entries and then subtract the product of these two entries. So there's 7 times 9 minus 4 times 10. That's the orange part. Plus. The green part is -2 times these two entries minus these two entries. So that's 3 times 9 minus 4 times 4. Plus, here again we get a 1. And now we have these two entries minus these two entries. So that is 3 times 10 minus 7 times 4. What do we get in the end? So 7 times 9, that is 63, minus 4 times 10, that is 40. So we are left with 23 here. Plus 3 times 9, that's 27, minus 4 times 4, that's 16. So that's 11 times minus 2. So that is minus 22. And the last entry here, that is 3 times 10 is 30, minus 28, that's just 2. So the final result, 23 minus 22 is 1, plus 2 is 3. So that determinant is 3. And of course, I've tried to illustrate all small steps of this process now, so that you will hopefully get a good idea of how this works. Of course, you don't have to do that anymore once you get the hang of it. And I will not do that anymore in the future as well. So we'll considerably shorten the process. And as I said, we'll also talk about other means, other methods of computing the determinant. And of course, we'll choose whatever method is most convenient. This will be in one of the upcoming videos. And of course, I hope I'll see you then.